Hey time travelers, this is gonna be like a short video. I think when I was grading homework number 2, I just sort of recognized that because it's like a fast summer course, whereas I was taught like, here's like everything you need to do about FBDs, and I like fell on my face over and over and over. You guys don't really get that opportunity, so I thought I should just make a video and just sort of throw down kind of literally everything that I know about like conventional standards around FBDs. Of course, as you saw, like an FBD works as much as you use it, so there's a lot of you that drew it like unconventionally, but you still used it properly, so it doesn't matter at the end of the day. But these are things that make it a lot easier to read, to use, and especially for me to grade, because like you'll see. So what you're going to do is you're going to start with a point. So unlike a diagram, so let's a lot of people, Jesus, chillax. Let's do a car. A lot of people did something like this, where they would draw the car and they would apply the force kind of where they thought that it would be. So there's like the force of the tires pushing it forward. There's a force of friction pulling it back. There's a normal force of the ground pushing up on the car, and the car pushing down on the ground with gravity. And these are like the main forces. Oh, here is a neat trick. When you want to show that forces are equal, all you have to do is like put a dashed line between them. But this is not an FBD, or like it's not a traditional FBD. And traditional FBD is you're gonna have a point. You're gonna draw a curved arrow to that point. You're gonna say, this is my object. So in this example, it's a car. And then you're gonna add your forces to it. Oh, I feel like I'm getting that. Okay, you know what? It's been done. So we're gonna say our weight force is about two lines long. And our normal force is also gonna be 2 lines long. We're gonna put a dash to represent that they're about the same. One like notable thing where this could have been really helpful is when you're talking about forces which are almost the same. So for example, a box is being pulled by a rope, and it's a 10 Newton weight box, and this rope is pulling with a tension force of 1 Newton. This would be our diagram, but it wouldn't be our FBD. So our FBD would be this. I'm gonna say our box. Oh, I actually never finished this out. A lot of people called this the friction. Pretty much no one said it was a friction force of the tires on the ground. While traditional FBDs will have you say like normal force, weight force, and like friction force, and have you abbreviate it. I will always say, like, if you say it's not the friction force of the tires, it's the force of, throttle, for example. That's fine. That is, if throttle is what's the force which is pushing you forward, like that's, like, I can't really argue with that. That works. So anyways, for example, with this box, what we can say is we have a normal force, which is this, and a tension force, which is this, and a weight force, let's draw it a little bit bigger, which is this. We can say inequality by having them with different dash lines. Because if they had the same amount of dash lines, these forces would be equal. So this is going to be your traditional FBD. You're going to have your curved arrow to your dot, and you're going to have your forces coming out from your dot. Additionally, traditional FBDs will be unresolved. So for example, if I have a box on an axis, there's some of you guys who put axes like this. This is fine, but as you can tell, it gets really messy really quick. So what I was taught is you have your axis, XY, and then you have your FBD as well. So we're gonna have an FBD for the box. And then we can say weight is down, friction, normal. That's just something that helps like make it really clear. There's some people, especially people with iPads, who could like adjust to make this really thick. That's kind of the only way I see around that. Because otherwise it's kind of hard to tell what's going on. And then my last note is that these are for your standard FBDs. When we talk about torque and stuff, we're going to use an extended FBD. So all of these treat the force as if it's happening exactly on the center of mass. And a lot of the times, you can do that. So because the weight force is directly on the center of mass. So for an extended FBD, so for example, if I have a rod, which is suspended by a rope, so we can say tension force equals like 40 newtons or something, and we have a length of 4 meters. This is the time where we would say our extended FBD looks like this, where we have, sorry, holy shit. We have our tension force like that, and we have our weight force like that. Because then you need to go from your axis of rotation and calculate R. I don't know if you guys have done torque yet. I actually haven't checked. I'm kind of behind on things, and that's okay. But this is like with an extended FBD, that's when you wouldn't do this. But most of the time, when we say FBDs or just you want a starting point, it's going to be this. So extended FBD for torque / rotation only. And then you can also think about these in the sense that for most rotation problems, you're not going to be accelerating the whole object in one direction or another. So that's kind of your clue into maybe it's an extended FBD if it's clearly rotating. Otherwise, the standard FBD is where you're going to go. Yeah, so to recap, you're going to have your curvy arrow to your dot. You're going to have all forces coming from the dot, no matter how many forces there are. And you can assume standard XY, but if your XY is different, you can put the axis separate to your FBD. I hope that helps. Now is the time where if you have a question on a concept that you want me to do a video of, please send me an email now rather than like at the end of finals week, because I will also be preparing for finals and I can record a bunch of videos now and I might have less time later. So yes, with that being said, I believe in you. You got this. You guys are all doing really good work. Good luck trying, travelers.